Hello, and thanks for checking out Chemistry Connections on the Hopewell Valley Student Podcasting Network, a proud partner of hvspn.com, where students come together to publish content to share with the world. The opinions represented within this episode are those of the content creators only. Please enjoy the show.
Hey everybody, in this AP Chem series video, we are going to be taking a look at the processes that take place in the sun through a chemistry-focused lens. I'm Sathya, and this is episode 13.
And I'm Tyler. Alright, let's start at the very beginning of the process of how stars get created.
So before a star is born, there are clouds of dust in the area where it will be formed. When clouds of dust begin to be pulled by the force of gravity, gaseous stars begin to be formed. As gravity drags these gas particles together, making stars, the temperature in the core increases to very high temperatures. As the amount of thermal energy in the core increases, the temperature also increases. As the temperature increases, the average kinetic energy in the sun's core increases, and according to the equation, Ke is equal to 0.5 mv squared. As kinetic energy increases, the velocity of the hydrogen atoms in the core increases. According to the collision theory, when a particle collides with another particle with enough activation energy, a bond may form, releasing a ton of energy.
Okay, so since the temperature is so high, does that mean that the hydrogen atoms within these stars will maybe begin to collide or form a bond?
Technically, since the hydrogen particles are protons, two protons coming close together have a repulsive force between them by Coulomb's law. Since both the protons are positively charged and particles with the same charge repel each other, Coulomb's law states that objects with the same charge repel each other, and objects with an opposing charge attract each other. This attraction, also known as electrostatic force, and repulsion are directly proportional to the distance between the particles and the charge magnitude. But the strong nuclear force overcomes this repulsion between the protons, and the two protons bind together to make a helium atom.
But wait, that's really only the first step of this process in which hydrogen atoms become helium atoms through fusion. It's actually a multi-step process called a proton-proton chain reaction. So how it works is first two hydrogen atoms collide together through the power of this force called the strong nuclear force. And these are basically just protons. So when they collide together, it forms hydrogen 2, so one proton and one neutron. We'll get back to that idea of how it changes to a neutron later on. So you have a hydrogen 2, and then there's another hydrogen 1 that comes in, so another proton collides with the hydrogen 2. That'll create what's now helium 3. So it's two protons and one neutron. And then when two of these helium 3s collide, this will produce the final product, which is helium 4, which is stable, and it also produces two protons.
A proton is composed of an up, and down quark. These are one of the fundamental particles of the universe. So everything the school tells you is actually a lie.
Whoa.
Not everything necessarily, but...
Sure. Not quite everything,
but like...
most things, maybe most.
Okay, that's a lie too. Okay,
yeah,
anyway.
Yeah.
I remember back in, third grade, they told me that a molecule was the fundamental building block of the universe, right?
True, yeah.
And I'm like, okay, yes,
okay,
more.
You're
just copying everything I say.
Yeah, I was thinking that too.
All right?
Yeah.
And then, what is it, 6th grade or something?
Yeah,
they taught us
atoms, right?
Yeah, they taught us about atoms. That atoms make molecules, all right. But now quarks make atoms?
What?
No. Even before the atom, there's like protons and neutrons. What? And then quarks make up these protons and neutrons? What is the actual fundamental particle of the universe?
That's pretty fascinating in my opinion. So when this weak nuclear force is applied, this causes an up quark to become a down quark, thus changing two of the particles from protons into neutrons.
Yeah, there are also 4 other fundamental particles: strange quarks, charm quarks, top quarks, and bottom quarks.
But we're not going to worry about those. What's important is that up quarks have a charge of positive 2/3 and down quarks have a charge of negative 1/3, which means when 2 ups and 1 down come together, this forms a proton, and as we know, this will have a total charge of +1. And similarly, since a neutron has 1 up and 2 down quarks, this will have a charge of 0.
These quarks make up the fundamental particles of the universe, such as neutrons and protons. Anyway, the protons are brought together by the strong nuclear force and joined together by the strong nuclear force. The quarks are joined together by gluons within each proton. The strong nuclear force brings another proton towards the proton, and then the protons collide with enough force. The protons stick together because the strong nuclear force joins a gluon to the quarks within the other proton, causing the protons to bind and form a helium atom.
Oh, okay, I see. So the sun conducts nuclear fusion within its core, and these interactions that occur between these quarks are central to the fusion process.
Yes, and I'm sorry, I didn't mention this before, but each quark is also bound together by these things called gluons, but I'm not going to get too deep into those. When the protons fuse, one helium atom is created. The fusion releases a bunch of thermal energy. When bonds are formed, energy is released, and to break these bonds, energy is required. Forming a bond through the strong nuclear force releases a lot of energy because the strong nuclear force is so strong at that microscopic scale.
Okay, yeah, that's interesting. So in the sun, I saw this statistic that about 74% of the mass is composed of hydrogen, and another 25% of the mass is composed of helium. So pretty much the entire thing is just those two elements. But you know what that means?
No, what does that mean?
That means we could use stoichiometry to figure out the mole ratio between these two elements within the sun. Remember, so as we determined before, the isotope of helium found in the sun is helium-4. So using the numbers that I said before, if we had a 100-gram sample of sun, then 74 grams would be hydrogen and 25 grams would be helium.
But since helium is 4 grams per mole, this means 25 grams of helium equals about 6 moles of helium.
Yeah, exactly. So when you look at the ratio of 74 moles of hydrogen to 6 moles of helium, that comes out to being about 12 moles of hydrogen per mole of helium within the sun.
Dang, that makes actual sense.
Yeah, I mean, thinking back to the proton-proton chain reaction, 6 hydrogen-1 atoms were needed in the fusion reaction just to produce a helium atom, and also 2 extra hydrogens were produced. So it makes sense for there to be many more moles of hydrogen than helium in the sun.
All right, so let's get back to the topic of pressure. PV is equal to nRT is the ideal gas law, where P is pressure, V is volume, N is the number of moles, R is the gas constant, and T is the temperature. According to this law, when temperature increases, pressure also increases.
Oh, so as the temperature increases, the core of a star will exert pressure outward.
Yeah, as this pressure opposes the force of gravity. Since the force of the reaction and the force of gravity are equal and opposite, the star is held in a delicate equilibrium and does not collapse in on itself.
Okay, that's really interesting how the forces have to be balanced, but obviously the sun is extremely hot. How does all of that heat energy get dispersed?
Our sun has a surface temperature of around 5,778 Kelvin. According to the second law of thermodynamics, entropy will always naturally increase in the universe. Entropy is the amount that heat is dispersed or spread out. Since entropy must always increase in the universe, the sun must disperse/transfer its concentration of thermal energy in some way. In space, stars transfer this heat through radiation, since convection or conduction is impossible in a vacuum, which increases entropy since the heat is more dispersed throughout space.
Wow, that's so interesting. This is a great application of the ideal gas law, since the intermolecular forces between the hydrogens and heliums are so small. I mean, I guess there would be London dispersion forces, but these elements that we're dealing with, they have such small electron clouds that are barely even polarizable, so their behavior must be so close to that of an ideal gas, and they're moving at such high speeds that I guess IMFs wouldn't play much of a role anyway.
Although it is the lightest and most abundant element in the universe, hydrogen is finite. The fusion in the sun is represented by the transmutation equation. One atomic number, one atomic mass number, hydrogen, plus one atomic number, one atomic mass number, hydrogen, equals 2 atomic number, 2 atomic mass number, plus heat. And if you notice real quick, this reaction releases a bunch of heat right? And as I said, in PV is equal to nRT, as thermal energy / temperature increases, pressure also increases. And this pressure is actually exerting an outward pressure. This outward pressure, again, opposes the force of gravity, which keeps the star in equilibrium. Also, if you look closely, you'll notice that this transmutation equation is actually uses isotopic notation. Isotopic notation is where the mass number, amount of protons and neutrons, is written on the top left of the element symbol. The atomic number, the amount of protons, is written on the bottom left of the element symbol. Protons dictate what element an atom is. For example, if a particle has only one proton, it's a hydrogen atom. And if it has two, it is a helium atom.
Oh, I noticed that you listed heat as a product in that equation. So this indicates that the reaction releases energy or heat, and it's exothermic, so the enthalpy or change in heat energy is negative. You also mentioned that hydrogen is finite. What does that mean?
That means hydrogen is a limiting reagent, which means it is the reactant that limits the amount of product produced within this reaction. When the hydrogen atoms run out, the reaction stops.
So at that point, if the reaction stops, no more thermal energy can be created.
According to PV is equal to nRT, thermal energy decreases as T decreases and P decreases. There will be no more outward pressure created, and the gravity becomes the dominant force in the star. The star collapses in on itself and explodes in a supernova. More entropy, since the explosion spreads out the rest of the heat, the rest of the thermal energy in the sun.
Oh, so that's how supernovas happen. I see. So when the star runs out of hydrogen to use in the fusion reaction, the pressure decreases because thermal energy runs low, and temperature decreases in the core, and the star collapses, so it just disperses all of its energy because of entropy. Are there any other ways that a star can die?
Actually, yeah. While our sun itself is not massive enough to go through this death, other massive stars can actually die another way, black holes. Density is equal to m over v, where m is mass and v is volume. As the star dies, it expands and sheds some of its mass. The core, however, maintains most of its mass, and when the star is massive enough, meaning it has a lot of mass, it doesn't necessarily mean it's large, it just has a lot of mass or matter within it. It has the ability to become a black hole. As the star collapses due to gravity, the volume rapidly decreases while the mass in the core stays relatively constant.
Wait, if the volume is rapidly decreasing with mass staying the same, that must mean the density gets extremely high.
Yup, at about 2 times 10 to the 19 kilogram per cubic meter, the star has enough density to become a black hole, which terrified me as a child, but fascinates me now.
Whoa, okay, that was so interesting to learn about. I mean, the topic of stars was mostly your idea, so I'm wondering, how did you come up with the topic?
Well, I never really understood how the sun worked, and fusion itself, so I wanted to explore something I didn't know. I knew that fusion would be something that we'd have to go into and learn about, and I also knew that we had to learn a little bit of quantum mechanics. And because I was too lazy to learn this stuff by myself, I decided to force myself to learn it through this project.
Yeah, I mean, that's a good point. I didn't know anything about the sun going into this project either, even though I guess it's a pretty big part of our lives. One detail I kind of skipped over is that in the proton-proton chain reaction where the protons are fused together, in the process of when the weak nuclear force changes a proton into a neutron, one other product, actually there's a few other products that are created, but one of them is gamma rays. And when leaving the sun, these get converted into lower energy photons such as ultraviolet rays, which can cause sunburn. Fascinating, right?
Wow, I didn't know that. I also wanted to know what fusion exactly was and how it worked. I also got to learn about quarks and how they are technically the fundamental building blocks of matter.
Yeah, I mean, at the start of the project, I came across an article titled, "Proton contains more anti-down quarks than anti-up," and I thought it sounded extremely dumb, but now that we know about quarks, things like this are able to make maybe a little bit more sense.
Honestly, I don't think either of us still get what it means.
Yeah, okay, yeah, true.
Anyway, thank you for listening to this podcast of Chemistry Connections. For more student-run podcasts and digital content, make sure you visit www.hvspn.com. And we'll see you next time.